Okay, so we're going to talk about trigonometric derivatives. Finding the derivative of trig functions is your objective through this lesson. And trig functions are sine, cosine, tangent. They do have derivatives, okay? So let's recall what a derivative is. The derivative of a function is a graph of its slopes at each point of the function that really come together and make a new function, okay? So, consider the function y equals sine theta, or sine x, okay? We can make a graph of the slope. So sine x here is this purple line, which printed off blue for you. Okay, so at 0, 0, that's sine x, and then we have the orange one on my paper, which red for you guys. That is the derivative, which is cosine x, okay? But if we looked at sine x and we looked at each x point here, and we looked at the slope, let's see what happens. So if the slope is 0, it looks like these are probably the easiest to look at. If you count the slope here, it's going to be 1. So the derivative at 0, the slope is 1, okay? Then at pi over 2, that slope is 0 because you have a horizontal tangent. Okay, that slope is 0. So that would have to be 0 on my derivative. All right, and then if you look at your other minimum here, okay, that's also a 0 slope. So my derivative would have to be at 0 there. Okay, and if you connect all the dots, now you have a new function, which actually happens to be cosine theta. Okay, so this orange graph here, or red on your paper, ends up being a brand new function, which is cosine theta, okay? It has to do with the periodic table that trigonometric functions follow, okay? Because they repeat after every pi or 2 pi, depending on what they are. Okay, so if you were to draw out the slopes of all of these trig functions, which we obviously don't want to do, then connected the points, it would make a new function, okay? But we're just going to say what these derivatives are, and you need to memorize them, or I guess not, since you guys can use your notes, but it's just basically a memorization here. We just said if we connect all the slopes of sine x, you're going to get the same graph of cosine x as cosine x. So the derivative of sine x is cosine x. Okay? If you were to do the same thing with cosine x, take a graph of all its slopes and connect them, it would be the same graph as negative sine x. So that's its derivative. Okay? Tangent, that derivative is secant squared x. That's the graph it makes. Okay, so we have derivative of sine x is cosine x, derivative of cosine x is negative sine x, derivative of tan x is secant squared x. Okay? All right. Then we have our other 3 trig functions. Cosecant x, that derivative is negative cosecant x, cotangent x. Okay. And derivative of secant x is secant x, tangent x. Okay. Then the derivative of cotangent x is negative cosecant squared x. Okay. And now these end up being different because a cosecant x, secant, and cotangent are all forms of sine, cosine, and tangent, right? So then you get into using power rules and quotient rules and simplifying. So that's why these end up being a little bigger for cosecant and secant, or longer, I should say. Okay, so those are the derivatives of your 6 trigonometric functions. Okay, so here's a little trick of how these derivatives go together. Okay, think about if you are, pretend you are leaning over to a friend and asking them, psst, what's the derivative of blank? Like you're cheating on a test, which I know you would never do. So the last 3 letters of psst, SST, are very helpful in remembering the connections between trig derivatives, okay? SST. So if you look here, secant, tangent, that's your SST, and your other SST below is cosecant, negative cosecant, cotangent, okay? And what that means is, well, the derivative of secant x is secant x tan x, and the derivative of tan x, if you go backwards, is secant squared x. So it's just kind of a way to remember. So if you look forward for secant x, it's the derivative of secant tangent x. And if you look backwards from tangent x, the derivative is these two, secant squared x. Okay, and the same thing kind of happens with cosecant. All right, so if you go forwards with cosecant, the derivative is negative cosecant x, cotangent x. Sorry, there's a lot to say here. I'm getting tripped up with my words, but if you go backwards for cotangent x, the derivative is negative cosecant squared x. So that's a nice little trick to remember. Okay, so we're gonna find these derivatives, and we can't forget about our chain rule, our product, and our quotient rule, and obviously the power rule is the most basic rule we have to follow. Okay, so if we look at number 1, what's going on here is this a composition of a function. It's sine and then there's a function within it. So that means we have to do a chain rule, okay? And I'll just do it the long way out so you can see. This would be sine of 5x to the first power. So if we did the chain rule, you would have to do 1. Remember, you bring the power rule now. You bring the exponent forward. Sine 5x to the 1 minus 1, 0. Okay. So that's really going to go away because it's to the 0 power. Times the derivative of the inside. Okay, so now we have the inside derivative. Okay, and within that we have a chain rule too. So the derivative of sine x is cosine x, but you keep it cosine 5x because that's really your x there in the rule. Then times the derivative of the inside, 5. Okay? So this all goes away, and y prime, or dy dx, equals 5 cosine 5x. Okay? So going back over that, the derivative of sine is cosine, if you don't want to do it that crazy way. The derivative of sine is cosine, okay? So I have cosine, this would stay the same, 5x, times the derivative of the inside, which is 5. Okay, so 5 cosine 5x. And from now on, if we have anything to the first power, I'm going to skip this power rule because it's just going to go to 0. But that was just so you could see it all out. Okay. Okay, so like for the next one, cosine, it's to the first power, so I'm not going to do that first step of the chain rule out. Let's just find dy dx. Okay, so the derivative of cosine is negative sine x. So everything is going to stay the same here. All that's changing is what's the derivative of cosine, which is negative sine. Okay, and then so this would be negative sine of 4x squared plus 3x plus 1. Remember, our chain rule says you keep this exactly the same. Then you times the derivative of the inside. So the derivative of the inside here is 8x plus 3, okay? So let's simplify a little more here. This negative 1, I'm going to multiply with my 8x plus 3. So dy over dx equals, well, you know what? We don't need to do that. We can just, since it's still being multiplied by another function, let's just write this. Negative 8x plus 3 together, okay, times sine 4x squared plus 3x plus 1, okay? So I just kind of rewrote that. You really could have stopped at the first step if you wanted to. Okay? Now let's do number 3. This would be the same thing as something to the third power. That's your exponent. So when this is just a power rule here. Okay, so I'm going to take my exponent down for y prime to the minus 1 power. So this would be 3 cosine 2, or cosine squared x, okay? That's following your pattern as if you had 3 as your exponent. But chain rule, now we have to times the derivative of cosine, okay? Cosine x. And I'll explain this real quick so maybe you can see it a little better. This is negative sine x, okay? So yeah, this ends up being y prime ends up being negative 3 sine x cosine squared x, okay? That's y prime. And let me rewrite this one way so you can hopefully see it a little bit better. Technically, our exponents should go right with the trig function, whatever it is. But if you want to think of this as y equals cosine x to the third, that may be a little bit easier for you to see. Because here's my little function. And the first thing I have to do with the power rule is take 3 times whatever that inside function is to the 3 minus 1, 2. Okay, the inside doesn't change. Times, chain rule, the derivative of the inside, negative sine x, okay? So maybe, and then we end up with the same exact thing. Okay, if you put the 2 here with the cosine. So that may be a little bit easier for you to see. Either way, we're getting the same thing. Okay, that's the first page.